By mass spectrometry, as shown on the right side of this diagram based on the graph, it says that the ratio of the naturally occurring oxygen-16 in yellow to that of the isotope of oxygen-17 is given to be in the ratio 4 to what? 1 respectively. And so it says here that assuming no other isotopes of oxygen are present, what is the atomic weight of oxygen? First, we need to review the concepts needed to determine the required variables. One is the mass number, next is the ratios, and later we'll look at the atomic weight. Now, let's look at the mass number. The mass number is the same as the atomic mass, and this here is defined as the sum of the number of protons and neutrons number in a nucleus of an atom, which is the majority of the atom's mass and where it is concentrated. Based on the question now, which is that for both oxygen 16 and for 17, these here are isotopes of oxygen due to both having the same number of protons but different number of neutrons, as shown here to be 8 for the proton number, but for oxygen 16 its neutron number is 8, and for oxygen 17 it is 9. However, for the next concept, we will use the mass number for each isotope. And the next concept here is ratios. And for ratios, this is a representation that compares the amount of different items. In this case, oxygen 16, which has 4 atoms, to the oxygen 17, which has 1 atom. Note that the ratio can come in different forms, like equivalent ratios. We have percentage to fractions to decimals. Therefore, based on the question, the ratio is based on the total number of items in the sample, where in fraction form we have the total number of items to be 5. For equivalent ratios, we multiply the initial total number by 10 to get 50 items as the total. For percentage, we multiply the initial total number by 20 to get 100 as the total. And finally, for decimal, we divide the initial total number by itself to get 1. Therefore, for both isotopes, for oxygen 16 and for oxygen 17, in here for the fraction, we have 4 out of 5 items that are for oxygen 16, and in here we have 1 out of 5 for oxygen 17. For the equivalent ratio or fraction, we have both fractions here to be multiplied by 10, both the numerator and the denominator, and that gives us 40, and we have 50, while for the other one we have 10 to 50. For the percentage, we have both fractions, numerator and denominator, to be multiplied by 20, and finally for the decimal, the numerator divided by the denominator to give us our value for the decimal. Now, this scale is important for the final concept, which implies what? The atomic weight. And the atomic weight here of an element considers 3 points. First is that it is the weight of 1 mole of a given element. Next is that it considers all the abundance of the element's isotopes using the average. And finally, this is expressed in U or grams per mole for the unit. Therefore, for oxygen in this question, we are going to consider the last 2 points. And looking at the second point, this here is based on the abundance of the element isotope. Therefore, there are 2 strategies that we're going to look at, and this here includes the following. First, fraction. In here, for each isotope, the fraction of the amount is multiplied by the mass number. And second strategy is for percent. For each isotope, the value out of 100 is multiplied by the mass number. Now, for the atomic weight, we add all the values together, and as you can see, we get the same value, which is 16.2. The unit of the atomic weight of the element is always in grams per mole, and the value is never a whole number but a decimal. However, this is not the theoretical value of the atomic weight of oxygen. Rather, the theoretical atomic weight of oxygen takes into account 3 isotopes that are, we have first oxygen 16, second oxygen 17, and finally oxygen 18. They are considered to be stable isotopes. Now, in terms of the ratio abundance out of 1, 0.997, next is 0.000367, and finally we have 0.00187 respectively, and each is multiplied by their mass numbers to give the respective values. And then for the final step, for the atomic weight, what we do is that for each value, they are added together to give the value to be 15.99 grams per mole, which is exactly what we see on the periodic table for oxygen.